Good morning, grade 11s. Welcome to week 6 of distance learning. We are starting a new unit. We're done unit 3. We finished all of that 2 weeks ago where we did quantities and introduction to the mole. Last week we did our final assessment for unit 2. We were hoping to do our full unit test when we return to school, but now knowing that we're best case scenario going to be back in the building in June, we did our 32 reactions assignment last week, which will count as your unit 2 assessment. So we're done unit 1, 2, and 3. We're moving on to unit 4. We still have unit 4 and 5 to finish before the end of the year. Okay, so we are in week 6. Make sure you've taken a look at the office hours. You know your calendar for the week. Do your reflection form for the week and continue to check out the frequently asked question sheet if you're having trouble with anything. Also, this will be open for you by the time you can see this video, but reminder, there is a new link that's been posted for you that will take you to Unit 4 resources, okay, which will have our activities for the week and again the calendar for the week should you so need it. Okay, but today we are going to be looking at lesson 1 of unit 4, which is Introduction to Solutions. So, there we go. This is what we're going to be taking a look at today, okay? So in your textbook, we're at section 8.1, 8.2, and 8.6. We are also going to be looking at page 370 to 379, as well as 398 to 402 if you're looking for specific pages from what we're going to be taking a look at today, okay? So, what's our agenda for today? We're going to start off by introducing what is a solution. Unit 3 is looking at solutions and solubility. So what are we going to be focusing on this unit? We're going to talk about something called molarity and a standard solution. We're going to then do a couple practice problems, and then you'll have a little bit of homework. You'll have 4 practice problems to work on to review what we did today. Okay. So by the end of the class, what students should be able to do is you should be able to describe characteristics of solutions and determine mass of solute, volume of solvent, or molarity of solution when given 2 of the previous 3. So if you're given mass and volume, you should figure out molarity. If you're given molarity and volume, you should be able to figure out mass. If you're given mass and molarity, you should be able to figure out volume. Okay. So today we said we're starting our solutions unit. So what is a solution? A solution is a homogeneous mixture. If you don't remember that term back from grade 9, homogeneous mixture is a mixture means it's made of more than one thing. It's not a pure compound or pure element. And when it's homogeneous, you can't identify the parts that make up that mixture, okay, by looking at it. So for example, if you have a cup of Kool-Aid, we know in Kool-Aid there's things like artificial flavorings and sugar and coloring, but it's not like I can say, oh, there's the sugar right there in my cup, or there's the color right there in my cup, okay? Same thing to like a cup of coffee. If someone makes me a cup of coffee and they put in cream and sugar and I say, oh no, I don't take sugar, I can't go in and pull out the sugar, okay, because it's homogeneous. It's different than something that's like a heterogeneous mixture. Heterogeneous mixtures would be more like something like a salad, okay? If you get a Greek salad and you don't like black olives, it's really easy for you to identify the components of the mixture, the black olives that you don't like, and pick them out because you can see all the components that make up that mixture, okay? So that's different than the coffee example where I can't identify it, okay? So like we said, a homogeneous mixture are those in which all substances in the mixture are in the same phase, but they have a uniform appearance, okay? And a sample taken from any part of the mixture should have the same composition. So a sip at the top should taste the same as a sip at the bottom as long as you've made your solution correctly, which is unlike a salad that we know some bites may have cucumber, some bites may have tomato. It depends on what piece you sample, okay? Specifically, we're going to be talking about aqueous solutions, and a solution is essentially made of one substance dissolved in another, okay? So that is called, a solution is made of what's called a solvent and a solute, okay? The solvent is whatever is in greater quantity, and the solute is whatever's in lesser quantity. So if you think back to the Kool-Aid example, if I make a glass of Kool-Aid, I may have a big cup of water and only put in a scoop of the Kool-Aid powder. Because there's no more water in my glass than Kool-Aid powder, the water would be the solvent and the Kool-Aid would be the solute, okay? Or again, if I'm making a chemical composition, if I'm making copper 2 sulfate solution, there's going to be more water than copper 2 sulfate powder. So water would be my solvent, and the copper 2 sulfate would be my solute. Okay. Water very commonly is a solvent in solutions, and we often call it the universal solvent. One, like we said, because it's a very common solvent, and two, because there's so many things that water can dissolve. There's a huge amount of compounds in comparison to other things that water can dissolve. So we call it a universal solvent. A lot of things. Not everything can dissolve in water. We learned that back in when we did, say, for example, our beaker assignment. But there is a lot of things that water can dissolve. Okay. So a lot of the solutions we're going to be talking about measuring or creating in class for this unit, water is going to be our solvent. Okay. Water is a very unique compound as well. Most molecules with a similar molecular mass to water are actually gases at room temperature and not a liquid. But again, this is often because molecules with such a small molar mass will be very small themselves because they'll be made of very few and very small atoms. And therefore they have really weak intermolecular forces. But we know water is a special example because there is so many opportunities. There's an opportunity at all three atoms that make up water to engage in a hydrogen bond. So that high amount of hydrogen bonds, and we know hydrogen bonds are a very strong bond, allow for really strong intermolecular attractions, which keep those molecules closer together in the liquid form versus the gas form. We learned this again back in Unit 1. We know hydrogen bonds are incredibly significant. There's a lot of unique properties of water that we can contribute to the presence of all that hydrogen bonding. So for example, they have very high melting and boiling points because those molecules are very strongly attracted to each other. So because of all that hydrogen bonding, so it's very difficult to separate molecules from one another to make them a gas. Water is also unique. It's one of the only compounds that expand when it's frozen instead of taking up less space. A lot of times when liquids turn into solids, the molecules get closer together, so they take up less space. Water goes into this special crystal arrangement, which actually makes frozen water take up more space than liquid water. You've probably seen this before if it's ever been hot in the summer and you put a bottle of water in the freezer, it sort of puffs up and expands. And that's the same reason why ice floats in water. So if you put a couple ice cubes in a glass of water, it's going to float because it's actually less dense, the ice, than the water. It's got a very high surface tension, which is why we can see like little insects that can walk on water, and that's because of the high amount of hydrogen bonding. They have a very high ability to exchange thermal energy with very little change in temperature, and they don't mix with polar compounds. Okay, a lot of these unique features are all explained in your textbook. This is right out of your textbook, and also outlined in this table here. But essentially, we're just saying water is a really unique solvent, and we're going to be talking a lot about it in this unit. So, where am I going to see solutions in my everyday life? All over the place, all around you, you're going to have solutions. Okay, a lot of the things that we drink, if you've had a pop or a soda in the last little bit, we know that solvent is water, and it's got lots of things in it. Okay, like flavorings, like colors, like sugars, like sweeteners. Coffee is a great example. If you drink coffee or tea, that's a solution. The cleaners that you use, a lot of the liquid medicines that you use are actually aqueous solutions. And a lot of these are going to have water as a solvent. Some examples may not, but solutions are all around you. Okay. So one of the things that we need to be able to measure when we're looking at solutions is their concentration. And the concentration is essentially how strong the solution is. So if you drink coffee, or mom or dad or parent or guardian drinks coffee, if you go to a restaurant and buy it, they may say, oh, this coffee is really strong, or, oh, I don't like this coffee, it's very weak. That's how much coffee or solute is dissolved into the solvent, which in coffee's case would be water. Okay, so if you have a really strong cup of coffee, you're going to have a lot of coffee in a smaller amount of liquid, water. If you have weaker coffee, there's going to be less coffee in the same amount of liquid water. Okay, so it's essentially a way of describing the ratio of the solute, what you dissolve, into the solvent, what's being dissolved into. If there's lots of solute in the solvent, the solution would be called concentrated. That would be like a strong solution or a strong cup of coffee. And if there's not a lot of solute in the solvent, we would call this a very dilute solution, or in everyday language, we would probably call it a weak solution. Okay, so like a weak cup of coffee or tea. Okay, so if we have something like, say this is blue Kool-Aid, or something like copper 2 sulfate, which has a color. When things are very concentrated, the solution's probably going to look very dark in color. So we can see here, there's lots of solute, which is the blue particles, for the same amount of solvent. Whereas something that's dilute, okay, or weak, is going to have much less solute, these blue guys, for the same amount of solvent, and that's why we can see it looks lighter in color. So the same way, if you put the same amount of Kool-Aid in a smaller amount of liquid versus a bigger amount of liquid, you're going to be able to see the difference in the color, and that's going to be reflected in difference in the concentration. So how we measure this in terms of chemistry, now when we're just making Kool-Aid or a cup of coffee, we're just usually describing it qualitatively, not quantitatively. So just by descriptors that we use with our senses versus numbers, we would just say, oh, it's a strong coffee or weak coffee. If we're in a chemistry lab, that's not good enough. We need to know exactly how much we're dealing with. So we're going to look at what's called molarity. And molarity is how we measure the concentration of a solution. Okay? So molarity is the number of moles per liter. Okay? So how many moles of your solute do you have in 1 liter of the solvent? Okay? So we would measure this like you put cm if you're measuring centimeters, and other mol per L, so moles per liter, a capital M, which also represents moles per liter, or you put a number in these square brackets, and that also tells the reader that you've measured it in moles per liter. Okay. In a lab, sometimes you'd be asked to create these. We're going to learn in the next couple of weeks how you would actually be able to create a solution with a specific molarity. But you also can purchase these if you're working in a really specific lab that needs a really high degree of accuracy. You may purchase a standard solution. Now, a standard solution is a solution that has a very, very precise and very, very specific molarity. And these are prepared using very, very detailed and specific measuring equipment with very specific volumes. So you can have a really high degree of confidence that if it says it's only 1 mole per liter, in exactly 1 liter, there's going to only be exactly 1 mole. Okay? So it's often measured in something that's a very specific container for measurement called a volumetric flask. And they'll come in these containers. We, for example, back at TDSS, not that I've been there, but since we've left, but we have standard solutions of different acids and bases that we may use in, say, grade 12 when we need chemicals with a very high degree of certainty of what their molarity is, when we're doing labs where your accuracy is actually tested. Okay. Or if I'm working in a pharmaceutical company or I'm creating a product, I need to know exactly what I'm putting into my solution or my reaction, so I need to be really confident in my concentration. Okay, so how do we calculate this? We would calculate this using a formula. Concentration, so big C, is always going to equal the number of moles of the solute divided by the volume of the solvent. Now, your moles is going to be in moles, and your volume, for the most part, should always be in liters, because what you're going to be reporting, your concentration is going to be reported in moles per liter. Okay, so if you're reporting it in moles per liter, the numbers that you put into your formula have to be in moles and liters. Okay, using this formula, in the same way we had the formula moles is mass over molar mass, from this formula we can determine the mass or moles of the solute, right? Because we could solve for N, and we can really easily convert N to mass if we need to. The concentration, again, we could solve for C really easy, just dividing N by V. Or if we knew the number of moles in the concentration, we can figure out the volume of the solvent. Okay. So let's do, let's do a question together. So I'm going to make myself disappear. Okay, so this says 44 grams of H2SO4, and you're given your molar mass here, which helps, is dissolved in 25 milliliters of water. What's the concentration of the sulfuric acid? Okay, so we're going to be trying to figure out concentration, which we know is moles over volume. Now remember, our moles needs to be in moles, and our volume needs to be in liters. Okay, so we need to do a couple things here before we can get straight to our formula here. First thing is we are given a mass, not a number of moles, but that's fine. Everything we learned in Unit 3 isn't going to go away. We can just say, no problem, I can calculate my moles of H2SO4 because we know mass divided by molar mass is moles. So I'm going to take my mass, which was given to me in the question, which was 44 grams. And I'm going to divide that by my molar mass, which is 98.08 grams per mole. That was given to me in the question, which helps out. So let's see, 44 divided by 98.08 is going to give me 0.4486 moles. The only other problem here too is my volume is given to me in milliliters, but I need it in liters. Okay, so 25 milliliters. Again, knowing that there's 1,000 milliliters in a liter is going to be 0.025 liters. Okay, remember we have to divide by 1,000 because there's 1,000 milliliters in a liter. Okay, so I just took 25 and divided it by my 1,000 to turn it into liters. So now I'm going to plug this in here. My concentration is going to be my moles, 0.4486 moles, divided by 0.025 liters. 0.4486 divided by 0.025 is going to give me 17.944. And I could write this as MOL per L. But again, with sig figs, if we look at the question, I am given 3 numbers here. This has 2 sig figs, both 4s. This has 4. And this guy has 3. So I'm only going to report to 2 sig figs. So this is going to be 18. Okay, I could write it as MOL per L. I could write it as 18 with a capital M, or I could write it as 18 in square brackets. Those all tell you that it's 18 moles per liter. Okay? But I reported my final answer to 2 sig figs because that's the least number given to me in my question. Don't remember that. Don't forget that from Unit 3 that we just finished. Okay? Alright. Let's try one more. This says household bleach is a 0.067 moles per liter solution of sodium hypochlorite, which has a molar mass of 74.44 grams per mole in water. What's the mass that you would need to prepare 225 milliliters of bleach? Okay, now it's asking me for a mass. I do know the formula, concentration is moles over volume. Now mass isn't in that, but I do know if I figure out moles, I can convert moles to mass very easily. We learned how to do that in Unit 3. So I'm going to first solve for moles, and then I'll convert moles into mass. Okay, so what's given to me in the question? It says the concentration is given to me at 0.067 moles per liter. That's my concentration. I don't know how many moles I have. That's what I'm going to determine to figure out my mass. But I do know the volume of my solution is 225 milliliters. Okay, which is the same thing if I divide that by 1,000 as 0.0225 liters. Okay, so I had to divide this by 1,000 to convert to liters. Because remember, this always has to be in moles and it needs to be in liters. So moles needs to be in moles, the volume needs to be in liters. Okay, so to rearrange this equation, I need to get rid of 0.225, so I need to multiply both sides by 225 liters. So that's going to leave me with 0.225 liters by 0.067 moles per liter is going to give me my number of moles. It's going to give me 0.0151 moles. Okay, now that I know my number of moles, I can figure out my mass, because I know mass is moles times molar mass. So my moles I just calculated. My molar mass is given to me in the question. If I multiply those two things together, it's going to give me 1.124 grams. And let's look at the question again to see how many sig figs I should report this to before I write my final answer. Neither one of these zeros have a number to the left of it, so only the 6 and the 7 are significant. So this is 2 sig fig. Neither of these zeros are significant. This is 4 sig figs, because they're all non-zeros. And here I have 3 sig figs. So again, I'm going to report this question to 2 significant figures, which is going to give me 1.1 grams. Okay, so what that's telling me is if I wanted to make a solution, okay, of NaClO, that was 0.067 moles per liter, and I wanted to make 225 milliliters of it, I would have to put into that solution 1.1 grams of NaClO. That's how I would make that solution. I would measure out 225 mils of water, put in 1.1 gram of NaClO, and I know I would have a solution of bleach of 0.067 moles per liter. Okay, and again, remember this stuff, this converting mass to moles and molar mass, that's not going to go away for the rest of the year. I did warn you that in Unit 3. And from now on, you don't have to ask me, Miss, how many decimal places should I put this to? We're always going to be reporting our final answers to sig figs, and you will be getting marks to report to the correct number of sig figs, just like you get marks for showing your work and showing your formulas, okay, previously. All right, so hopefully that makes sense. It's a simple formula, very similar to our mass and moles conversion formula. What I'm going to have you do, there's 4 questions that have been posted for you on a worksheet that can be found on Google Classroom. You can either complete those questions in the Google Doc, okay, if you're using computers, or like our previous homework, if you'd like to do it on a scrap piece of paper and take a picture and upload those, you can do it that way as well. Okay, hope you guys are having a great day. Hope you're staying safe, staying well, and staying inside. Hopefully we'll be seeing each other soon.